Okay, we're here today talking to Deep Prasad, a physicist from the University of Toronto, also the CEO of Reactive Q. Deep is working on the first generation of quantum computers, and he's also been very interested and involved in recent developments regarding the ATIP program, and he's been involved in online debates over whether or not the United States government is investigating possible exotic or who knows, even extraterrestrial material. Deep, thanks for joining us.
Thank you, Jess. That's a great introduction.
Okay, first things first. For those of us who don't know much more about computers than how to fire up our laptops, what is quantum computing and how is it different from the regular old computing we know? And if you could, please answer in 25 words or less using words with less than 5 letters. That last part was a joke.
All right, yeah, that's a hard constraint. But yeah, so essentially, the biggest difference is the kind of information quantum computers can compute that classical computers can't. In theory, like the favorite example that I usually use, that's very common in quantum computing, is the Shor's algorithm. So essentially, the problem that Shor's algorithm solves is a problem of prime factorization. And in the case of, let's say, RSA encryption, which is the kind of encryption that sort of backs the internet, it's the reason why you can cash in your money online and not get hacked. Like the internet doesn't get taken down by hackers every single day for this reason, amongst others. But yeah, so the only reason RSA encryption works is because it takes a very long time to factorize a number. And in the case of RSA, the number that you're given as your key, or like you can think of it as your personal lock, a safety lock.
Like a pin.
Yeah, perfect, exactly. So you're given. Imagine if everybody was given one of them, and it took, in the case of say 2048 digits, like a number that big, it would take nearly the amount older than the age of the universe to factorize that number with a traditional computer. So you're safe if you use RSA in that case. Like nobody's ever going to guess the correct number, and yeah, it would be pure luck if you could guess it. So the other way, right, is to do it through brute force. That's what takes longer than the universe. Like if you wanted to compute the
To
answer,
try to guess it.
yeah, you got it exactly. It's exactly like having a those like dial locks on a safe, and someone has no idea what say the 2048 digit password is, so they're just gonna sit there and guess all day. There are some ways to do it, but there's no getting around large numbers. But with quantum computers, we have algorithms that would let you do that in less than 2 seconds. So now we can do, yeah, exactly. Now we can do computations that were enormous, totally outside of our imagination, and we can actually realize them. So
Now, if I can interrupt for a second,
yeah,
is this all, and bear in mind, you're talking to a layman,
okay.
is this all software based or is there a physical quantum computer that works differently than the normal hardware we're used to?
That's a great question. There's absolutely physical hardware. Like it's fundamentally different. Like everything about it almost is physically different than the current computer. Like there's yeah, very few things that are recognizable, I would say.
Okay. Well,
Yeah.
that sounds good.
Yeah.
Having gotten that out of the way, I think most of us don't really understand the whole quantum thing. Can you tell us a little bit about your company and what it is you hope to accomplish and what ramifications that could have, for humanity at large?
Sure. So essentially, what we want to do is master the art of a digital simulation. So imagine being able to simulate a car in your on your computer, and you could simulate the appropriate physics that goes into developing it and testing it. This would like save you time and resources from building these prototypes in person, right? Because right now, all of engineering relies on building these physical prototypes. To an extent. Like there's what I would say a spectrum of engineering companies when it comes to simulations and how they use them. Some companies don't use them at all. And so these companies will spend millions of dollars building their next prototype before they offer their product a year or two later down the road. These companies are very used to like the old paradigm, I guess you can say, and they want to avoid using simulation. Then there's companies. Sometimes you'll find these in cell manufacturing scenarios where they basically design everything digitally, like every single piece of, like, say, a phone or a phone battery. This is just an example, might be simulated down to a huge level where you're only building the prototype, like the final one, that's it. So the problem seems easy, or so I thought at the surface, but then I found out that it takes an impossible amount of compute power to simulate the kinds of objects that we were interested in simulating. So we wanted to simulate exotic materials, metamaterials, superconductors, really essentially automate the idea of materials discovery, because materials discovery is mostly a trial and error process that's unavoidable, but we can reduce the physicality, like the actual, right, real life discovery part. And the only way to do that, though, is to characterize nature using the right algorithms. But nature, is quantum mechanical in nature. Like in basis, when you look close enough, it is quantum mechanical. So if you want to simulate anything of relevance, like a battery or an entire airplane, eventually you're going to have to address the quantum mechanics. So what my company is trying to do is bridge the gap between our world's most classical supercomputers, so just the most powerful supercomputer you would think of on Earth, like those kinds, and really even like classical compute in general, and bridge it to quantum computing when it comes to simulation.
See, I was picturing something in my head, and tell me if I'm wrong. Like in the old days, if you wanted to build a car,
Yeah.
somebody would draw it on paper, and then they'd go build a physical model and put it in a wind tunnel or whatever to see what the aerodynamics were. But you're talking about you can simulate all that and not have to bother building the model because you can do it in cyberspace. Is that close?
You got it exactly right. Exactly. So what we have to do right now is try to just push the current limitations that we have when it comes to simulating, like let's say wind in a wind tunnel. Like that was one of the first to go. So that's a great example. When computational fluid dynamics came along and computers became useful, like classical computers, yeah, absolutely. They replaced most of the wind tunnels at NASA, and we only hope to do that at a more, I guess, intense, granular, and cheaper level, and faster, of course. Because some of these simulations will take up to 6 weeks to run. So imagine being the guy who's in charge. You only have one shot, and it'll cost like hundreds of dollars or thousands of dollars in compute time to simulate a 6 week long simulation, right? Like we're talking, this guy has to turn on a computer and let it run for 6 weeks straight, then come back and hope that he set up everything right with his simulation. And so that's essentially right now, but until quantum computers get to a more mature stage, what we're doing is speeding up those simulations. So what might take 6 weeks, we can do in 1 week in some scenarios, and so on and so forth.
Last question on quantum computing.
Yeah, cool.
Is this still all theoretical, or are you already at the stage where you're physically doing this and working on it?
You got it. So it's at the stage. It's been there for like a few years where we're physically programming these quantum computers. So we're actually moving these qubits, and this is the first time we're think about it. We're controlling behavior at the atomic level. I think that's super cool, and we're actually using it to our advantage rather than just being wowed by it. We've decided to control another aspect of nature. So yeah.
That sounds a little scary. Okay, I want to transition a little bit. You made mention of something a little while ago that tied into what I brought up in the introduction about things like exotic materials. I've been following a number of interviews you've done, and I've been following you on social media. and looking at some of the debates that have been going on. And you have been expressing a lot of interest and engaging with people about these so-called exotic materials. Excuse me. We've done some coverage at our site about the recent stuff about ATIP, government revelations, and the possibility that maybe they are looking at some exotic materials that nobody's really quite sure about the origin of. I just wanted to get your take on this. What are your thoughts about what you know so far or suspect so far of exotic materials and whether or not those are things we could have created?
Yeah, so fair enough. That when it comes to exotic materials, I think we should define it just to be on the safe side. To
Okay.
me, a truly exotic material is not just one that came from outside of Earth. Like, let's say it has, so there's something called isotopic analysis. You'll hear me use that term a lot. And essentially, like, the way to look at it is just like it's a fingerprint. So Earth has a fingerprint when it comes to the isotopic analysis. So does our solar system, and so do other solar systems. That's how we can tell when, say, a piece of rock is either from Earth or from space, like outside of our solar system. And these methods of being able to tell these isotopic ratios through analysis are very, very well defined. We have mastered the art of that. So it's extremely safe when I claim generally that they say this like cup of water I have. The actual glass is made up of isotopes or an isotopic ratio, not from Earth. I can very easily prove that to somebody, and other labs with their own equipment can prove it too. So when it comes to exotic materials, I draw the line after that. So once we've determined that something is extraterrestrial, like that's actually a term they use, extraterrestrial in nature, like the isotopes, then what we do or what we should do is
You're not talking at this point about aliens. You're saying something that didn't originate on this planet because of its makeup.
that's correct.
Like it could be a piece of rock that came from Mars or something.
Yeah, so when it comes to exotic materials, I consider anything just past that. So like, it's not just that it came, say, from Mars or from like, I don't know, the Andromeda galaxy.
Another star. Yeah.
Yeah, exactly. It's also that it shows signs of engineering. If it does that, that's when my interest is peaked. Like, because then stuff like that is what you can scientifically go to and say, all right, you may not believe in aliens, but explain this. So like that's very powerful, right? I mean, that has to be done. Somebody has to do it, and I found that actually there have been a ton of at least scientists and people claiming to have materials that fit that criteria. It's just that because they're the mainstream material science community, the mainstream quantum physics, computational physics, like even the engineering community, these communities haven't come together to like basically bulletproof and scientifically analyze some of these metamaterials that people claim to have. They don't even consider or think about it, but whenever they do or whenever I bring it to their attention, it interests all of them. And the problem is that they've just never been engaged. They've never seen a serious reason to do their own investigation. And when they want to, they'll obviously get ridiculed like crazy. But so, yeah, essentially, when it comes to like these exotic materials research, what I think can happen, and it'll accelerate disclosure, we can maybe get into that later, is by having the community peer review an exotic material research paper and genuinely entertain the idea that it was engineered not on Earth. It's as simple as that. You don't have to go deeper, right? Like you don't have to say, oh, it came from this universe or a different universe, because we frankly can't rule that out. We can't also rule out that they were on this like planet when they made it. It's just made with tech that we don't have. But yes,
we saw descriptions, if you'll pardon me, coming from, I believe it was somebody who was looking at the latest release from To the Stars Academy, where they had material that some people thought they had just gathered up from farmers. other people believed it had come really from ATIP, materials that Robert Bigelow had gathered, and they were making claims about these tiny micro layers of material that didn't match certain things. To the best of your knowledge, has anybody confirmed these exist, or have there been test results from accredited labs released to say, oh yeah, that's something we can identify where it came from?
Certainly. And unfortunately, the main scientist who ran the lab there's one scientist who is still alive, though, and I'm sure a ton that I can name if I just went back to some of the videos. But there's a guy named Dr. Levengood. He did a test on putting the metamaterial, specifically the bismuth magnesium piece that Linda Moulton Howe has, in water. That's the one that performs electrolysis. Basically,
Oh, it splits the water into oxygen and hydrogen with no external energy.
you got it.
I
Exactly.
I heard you talk about that. That's
So,
amazing.
and he put his hat behind it. He's like, listen, man, I did it for 43 days. Could you imagine? Like, he just slept it in there and it kept doing it. That's crazy. So there are tests, so that I hope and that were either done and published in the paper or that we can do, because certain, like, if that was true, that's the implications are, yeah, they speak for themselves. But of course, that needs to be confirmed, right? Like, we need to just be super, super sure, check that it wasn't trapped gas. I think that idea is pretty stupid, but it needs to be ruled out regardless, right? So things like that. Once, yeah, like once you get past that, I don't know. I think, like, you can motivate other research labs, like let's say at MIT or U of T or Caltech, to then go and say, we'll do our own analysis on TTSA's material, and regardless of the truth, we'll post it. Because if TTSA has anything that's like legit, and like I've met a scientist at the SEU conference who's worked on this. He's like directly, yeah, handled it, and his experiments. He later backtracked and claimed that it was a stealth material, like it was made for some sort of stealth vehicle, like the bismuth magnesium, and it's man-made. But he didn't comment on the isotopic ratios at all or any of that. It was interesting, to say the least. But
I'll speak for most of my audience when I say that throughout the course of this interview, you've used a lot of words that most of us don't understand, but you are doing a good job of encapsulating. A moment ago, you mentioned the word implications, and you sort of given me a great lead into the next question I had for you.
sure.
Hypothetically, because I guess it hasn't been 100% established yet, hypothetically, if we did get our hands on that sort of material you mentioned that Linda Moulton Howe has or whatever, and we were able to figure out, if that's even possible, some way to fabricate it, what are the implications of that for mankind, for our technology, for our future? Is there something groundbreaking that could be a real game changer?
Absolutely, yeah. That's a great question. In the case of electrolysis, here's the thing. Hydrogen is the greatest energy dense element we have. It's the highest energy dense fuel source that's naturally occurring in nature. The problem is that extracting hydrogen is expensive. It costs more money to put in than you get out of it in terms of the power, right? So like it's super power intensive to separate hydrogen from water. You need like these massive plants, you need electricity, and after all that, when you scale it, yeah, you're totally losing money. It's not worth it.
Oh,
But
so it takes more energy to get the hydrogen out than you get out of the hydrogen, is what you're saying?
you got it exactly, exactly.
But
And
this
so
could do it for free?
yeah, well, essentially, like if we can
Well,
engineer it and
cheap.
just remove the cost of those materials. But yeah, exactly. You literally just drop in the ocean and you have an infinite amount essentially. Like it would easily, the amount of energy we would unlock would easily like address all of our current energy demands. They would look like a joke. And the best part is it's a clean reaction. So we're not talking about something that pollutes the environment when you use it. And I think that's fantastic. So you could have desalination plants that are powered by these devices that,
Wow.
yeah, create hydrogen and use that as a fuel source.
That would qualify as a game changer in my book. I'm not going to keep you all day, but I'm going to throw a bit of a curveball here at you at the end. Just this week, we saw there was a new interview with U.S. Commander David Fravor, who was one of the U.S. pilots who engaged what's become known as the White Tic Tac, and he was the one who recorded some of the video and was engaged in the part that was caught on radar. For people listening to this interview who aren't familiar, the White Tic Tac was an object that this pilot encountered in an F-22, which was, and I'm reading from this here, capable of hypersonic speed, as well as being able to hover 500 feet above the ocean, perfectly still, with no wings, no rotors, no jet exhaust, no heat signature. As a physicist, I would like to ask you, is this something that us in the United States, North America, the Russians, the Chinese, is that something we could have cooked up and kept secret from everyone else? Somehow the ability to apparently attenuate gravity? Or as a physicist, do you think we're just nowhere near that yet?
Yeah, I would say the latter because I'm not the kind of guy. It's ironic. What I'm going to say, but I'm not the kind of guy who buys into conspiracies. So, like, if somebody's going to try to prove or like convince me that there's a hidden black project, right, a hidden part of government, hidden part, right, you figured it out.
Something at Area 51. They figured out how to defy gravity.
You got it exactly, and it's like, all right, sure. Let's say that they did figure out how to defy gravity. The amount of power scales needed to defy it are huge. Anybody using that kind of power on our planet would leave massive energy signatures. We would have picked it up. We would know people are messing with gravity waves and creating them. It's like with let's say radio waves. Like when we first made them, and even now, we don't care where they went, right? And like if they sort of like leaked out into space. So if somebody's toying around with gravity waves and gravity wave generation on this planet, we would have picked it up at LIGO, for example, right? The gravitational wave detector in 2016 that picks up gravitational waves.
I'm familiar with that one, but I'm going to interrupt you again, and I apologize. You just said something that blew my mind, unless I misinterpreted you.
No, go for it.
So with enough energy, under your understanding of the laws of physics, you believe it is possible to attenuate gravity?
Yes, absolutely. The problem is that like it requires a ton of energy. If you're going to just assume that you know nothing more than what we know about nature in the mainstream. So, like for example, when it came to detecting gravity in 2016. 2016 was the first time we detected gravity waves. So that's like over 100 years after essentially Einstein had predicted it in his equations. And that was, so the reason why it took that long to detect these gravity waves is because gravitational waves are extremely weak vibrations in space-time. So like, you know how air vibrates? That's like a way to think of sound.
Sound. Yeah.
You have gravity that can do that to space-time. So it can move and vibrate space-time. It's an oscillation in space-time. And
so there's no such thing as gravitons? Gravity travels in waves?
We don't know yet. We actually still don't know if there are gravitons or there aren't gravitons. But what we do know is that classically gravity behaves like a wave. So it says nothing about whether gravity is a wave. That's different than it behaving like a wave in this scenario. So when we detected it, the ripple is very, very weak. It's so weak that you need a detector that's 4 kilometers long in length. And this signal that we detected, get this, it was 1.3 billion light years away, I believe. And it was 2 black holes spinning around each other and colliding into each other. And it took that level of energy to create that tiny little gravity wave in space-time. So in theory, you can do it. Like if you have a lot of energy, you can attenuate gravity and space-time. I just don't see how you can do it with oil. Like I don't see how you can even do it with anything this planet has to offer.
So I can lift my car off the ground if I can just get two black holes colliding underneath it.
And like times like 1,000 or 1 billion or something, like it. But yeah, that's right.
Okay.
Because like for example, the Navy patent, something I wrote an article about was it calls for this. It calls for gravity wave generation, something that we only know black holes to do, and it uses gravity waves bigger than what these black holes create in order to propel themselves. This is the Navy putting in an official patent from their top naval test base, right? So that's interesting. Like, why do they do that?
And yet, somebody that we trust in the military watched something hovering 500 feet over the ocean as if it was defying gravity with no black holes around. Interesting. I have a terrible feeling that we've probably just lost 3/4 of my audience. And I can't keep you all night. So I will just close by asking you, if people want to find out more about this, where can they find you online if you wish to be found, on social media, your homepage? Where can people keep up with you if they want to keep up with what you're doing on these various subjects?
Sure. At Deep Neuron, DEEP, NEURON. That's my Twitter handle. That's usually, as you pointed out, where I'm quite active. I think like the interesting thing, and this is why like it's great to be in our position, like to be having these discussions that we are today, is that some of this stuff is actually history in real time. It may not feel like it, but we're only ever going to get the opportunity to have these discussions once before the truth is finally out, and then it's just well accepted fact. So yeah, I think Twitter is like, I don't know, it might be looked at by historians one day. You never know.
There's a part of me that deeply hopes that you're right, sir. There's another part of me that's terrified.
Yeah,
but we'll see how that goes. All right, thank you again.
Yeah, thank
Deep,
you.
And perhaps if you get another big breakthrough, you can come back and visit us again.
I will, gladly.
Take care.